Welcome, dear students, to the seventh lecture on nuclear physics, the second in the beta decay process. Before I go to the lecture, let me just go through the quiz which I had asked in the previous lectures. Half-life of uranium 238, order of 10 raised to 9, that's the correct answer. The decay constant increases with number of atoms, decreases with number of atoms. Answer is more the number of atoms, more is the decay constant. The tunneling probability increases with increase in mass. Smaller the mass, greater is the tunneling probability. That is the reason why the beta particles have very little difficulty in tunneling through compared to alpha particles. For all practical reasons, electrons don't have any tunneling barrier. They are able to tunnel through the moment they are created. Okay, then we go to the quiz 6th. The daughter nucleus is same in which case? Positron and electron emission, beta emission and electron capture. Beta emission and electron capture, positron emission and electron capture. The answer is positron emission and electron capture. In both cases, the daughter nucleus is the same. So one is not able to say for sure whether the daughter nucleus has arrived because of the positron emission or because of electron capture. The only signature is if the electron gets captured from the lower orbit. If you have a nucleus like this, and if the electron is orbiting around, this is the electron orbiting around the nucleus, and if this electrons get captured here, there is a vacancy here, and the electron from the outermost orbit can come and occupy the lower shell, and in that process a photon can be emitted. Photon is equal to delta E by H. This is the difference of the energy of the two orbits divided by H is going to give rise to photon of frequency nu. So normally what happens is in electron capture is always accompanied by a gamma emission, because this energy falls under the gamma rays energy spectrum, and during the positron emission you don't have any gamma emission or electromagnetic emission. So that is the only way you can differentiate whether the daughter has arrived through the electron capture route or the positron emission route. Okay, positron emission can take place only if the difference in mass is greater than 2 MeV. This is the correct answer. For beta, because we have derived the expression for Q, please refer the expression for the Q for beta minus, beta plus and electron capture. You know that this answer option is true. The beta energy spectrum, the 2/3 have maximum Q, maximum number of particles have 1/3 of Q. This is the correct answer, and you can see that this was the graph we had discussed, and we had seen that graph or something like that. So this is the number of particles, so you can see that this is energy. This is almost 1/3 of Q. So this is 1/3 of maximum number of particles have energy, which is 1/3 of Q. This is your Q, or E max as you call it. The beta particles is in the range of 1 MeV. That's the correct answer. Which of the statement is false? The shape of the energy spectrum is different. The shape of energy spectrum for beta particles, the beta particles have no barrier for tunneling. The shape of energy spectrum form is same. Which statement is false? So the answer C is false. Actually the energy spectrum is different for alpha particles and for beta particles. You know that for alpha particles it is almost continuous, it is like this, and for beta particle it is like this. So there are two different graphs. The other thing is the alpha spectrum is discrete, in nature, while alpha spectrum is continuous in nature. Right. So, as the title suggests, that we are going to be discussing about the difficulties in understanding beta decay problem. One of the difficulties which we have highlighted so far was the continuous energy shape of the beta particles, and beta processes, as we have seen, that when there is a beta emission, it is nothing but electron. Beta plus means it is positron. Right now we are not talking about the neutrinos, that we will see a little later. Right. Now this is the continuous nature of the beta spectrum, which we had difficulty in understanding. If this is continuous in nature, the expected energy of all beta particles is around Emax, and the little difference other than the Emax would be accounted by the gamma emission. But to our surprise, you also have certain number of particles which has got zero energy. You can see that. So the energy varies between 0 to up to Emax. It has energy variation from 0 to Emax. So this is a continuous energy values taken by the beta particles from 0 values to Emax. So that was the difficulty in understanding the energy spectrum of the beta particles. So the question was, what happens to the remaining energy? For example, if beta energy is here, then what happens to this difference? How do you account for this difference in energy between the Emax and the energy carried by the beta particle? So the law of conservation of energy was in danger of being violated. There were different theories, as we had discussed in the previous lecture, proposed that the remaining energy is carried by the photons. The other possibility was the electrons which are there in the outermost orbit, they must be taking away this remaining energy. But in the calorific experiment means the experiment in which the heat is measured, the difference in the energy was not observed. For example, if the total Q is around 1 MeV, and if the beta energy is around, let's say, 0.5 MeV, then the question was, what happens to the remaining 0.5 MeV? Who takes away the remaining 0.5 MeV? Or if the energy of the beta particle is 0.3, then what happens to 0.7? If the beta particle energy is 0.2, then who takes away the remaining 0.8 MeV energy? So these are all very high values of energy which can be measured in any experiment. So the question was the missing energy to be accounted in a energy spectrum of beta particles. And the other thing which is also often this was continuous, while alpha spectrum, as you can see, was discrete. It was divided into 4 groups, 3 groups, 5 groups. So they're all discrete, they are not continuous values. And the alpha spectrum was understandable because finally it landed up in the energy levels of the daughter, which are not continuous but discrete. Since the energy levels of daughter is discrete, one could understand that the energy carried by the alpha particle is also discrete. But then this is a continuous energy distribution. So these are all one of the major difficulties in understanding beta spectra. Now we'll see the other two problems which are also equally important. There are certain sacred laws in physics, like law of conservation of energy, law of conservation of linear momentum, law of conservation of angular momentum. Now these are all things which can never be violated in any of the processes. Any processes, whether it is subatomic process or macroscopic object, anything, the conservation laws, basic conservation laws cannot be violated. So what we have seen earlier, the conservation of energy being violated. Now we'll see that even the conservation of angular momentum was under threat. Now let's understand this equation. This is one of the beta minus emission. 1H3 isotope of hydrogen gets converted into helium-3, which is one of the isotopes of helium, and beta minus particle is emitted. Now let's understand this nuclear reaction. Now what happens is angular momentum of any nuclei is given as IH cross. It is given as IH cross, where I is an integer including 0, which means the angular momentum of any nuclei, that is for even nuclei, this is for even nuclei. So for even nuclei, the angular momentum can be 0, H cross. So the values it can take is either 0, it can take H cross, it can take 2H cross, like that. It can take different values of integers if there are even number of nuclei. But if there are odd number of nuclei, then it is odd multiple of H cross, odd multiple divided by 2 of H cross, which means it can be 1/2 H cross, 3 by 2 H cross, 5 by 2 H cross, 7 by 2 H cross, 9 by 2 H cross, and all that. So for odd nuclei, it is odd multiple of half into H cross, and for even nuclei, it is an integer multiplied by H cross. This is the angular momentum of any nucleus, which is very well known. We have seen this in your properties of nuclei in first year. Now let's look into this equation here, nuclear reaction. Here you can see that there are three nucleons. So the LHS should be odd into half multiple of H cross. Okay. Now there are two nuclei here. One is an odd, another is even. So RHS is odd into half multiple of H cross multiplied by half H cross. So this becomes even multiple of H cross. So you can see that the angular momentum is not conserved. So this is a big problem. Now people had no idea about who's taking away this remaining energy, what is this particle, and there was a whole lot of dilemma about it. So we are right now talking about around 1930s and so, where the third particle was not proposed. So the angular momentum conservation was under a serious threat. This is the second difficulty in understanding the beta process. The third was linear momentum. Now you know that linear momentum is conserved. I think the very famous example of bomb exploding. So the total linear momentum before the explosion is 0, and the fragments fly off in different directions. So when you add their momentums, the momentum should also be 0 after the explosion. So before or after the reaction, the linear momentum should be conserved. Now if this is lying without decay, the linear momentum is 0. Now supposing here it decays into He3 and electron. Now what was observed in the Wilson cloud chamber experiment, where you know that when the particles move, they leave behind droplets, or in bubble chamber they leave behind. In bubble chamber they leave behind the processes. In a cloud chamber you have the cloud formation, and here you have the water droplets which are there in beta chamber, this bubble chamber. In any of this experiment, what was observed is that the angle between the parent and the electron, the daughter which is formed, He3 and electron, they were not flying off in opposite direction. What is expected is that they should fly off in opposite direction like this. If electron is moving in this direction, then positron should move exactly in opposite direction. So what happens is this degree angle should be 180 degree. Now if you add their momentum, you know the vector addition of two vectors in opposite direction is 0. So if this moves in x-axis, this moves in minus x-axis, or if this moves in y-axis, this moves in minus y-axis, or z-axis or minus z-axis. In either of these cases, the linear momentum is 0. But what was observed is there was a little angle here between the two, and the angle was less than 180 degree. The whole idea was, so the linear momentum also stood violated. And to solve this problem, Fermi, the great Pauli, German physicist, he proposed a particle called neutrino. Now, dear students, look at the genius of this man. He is a theoretical physicist. He doesn't know anything about experiment, but he said that the missing particle is taken away by neutrino. He just proposed one thing to save the law of conservation of angular momentum, linear momentum, and energy. So the missing energy is carried by neutrino. So to make the triangle in such a way, the momentum triangle in such a way that the total momentum is zero, then you have the neutrino into the picture. Angular momentum also, if you have the third particle, then the angular momentum gets satisfied on both sides. So he in 1930 to explain beta decay problem, he says where an invisible particle was taking away a fraction of energy from emitter. Pauli predicted this particle to be neutrino. It is the symbol of neutrino is like this. There are two types of neutrino, neutrino and anti-neutrino. I'll talk about this little later. So what is this neutrino? We'll look into this. So here you can see, here neutron is decaying into electron. This is proton, and there's a third particle involved in beta decay. And very interesting that along with electron you only have anti-neutrino. Please register in your mind. I don't know what to do. You remember this, you put it down in paper. With electron it is always anti-neutrino, and with positron, if it is a positron emission, then it is always accompanied by neutrino. So this is there. If it is electron, then it is always anti-neutrino. Now, why is this so? The answer to this you will not get until you study a course in particle physics, which you will study in next semester. So right now, for time being, you just have to remember that electron is always accompanied by anti-neutrino and positron is always accompanied by neutrino. Both of them were proposed by Fermi. Of course, when he proposed it, he never knew the difference between the neutrino and anti-neutrino. He just called it as a neutrino. So here you have the beta decay, beta particle flying off in one direction, the daughter flying off in other direction, and to make the momentum triangle zero, you have the neutrino, which are invisible. That's why it's shown by dotted lines. You can't see them, and why you can't see them, we will look into the next slides to understand why it's called invisible particle. People also called it as ghost particle. Ghost particle means a particle which is not seen but its presence is felt. I called it as a ghost particle also. Physicists call it them as neutrino as ghost particle also. And this solved all the problems. So theoreticians were very happy. Okay, fine. So we don't have to discard. We have got a solution for conservation of energy, conservation of linear momentum, conservation of angular momentum. So this is the whole thing here. You can see the same shown in different graphics, right? And why is the electron nuclear continuous? Third particle neutrino is taking away part of the energy. So dear students, if energy of electron varies from 0 to Q, then opposite, the energy of neutrino should vary from Q to 0. So the whole idea is Q can be nearly, I am using the word purposely, is nearly equal to the energy of electron plus energy of neutrino. Because I am discounting the very small recoil energy of the daughter. The daughter is very heavy, so it's not going to fly off with great speed. Now the lighter particles are going to move with great speed, so bulk of the Q is going to be taken by the lighter particles. Remember in alpha particle also we had seen, alpha particle is much more massive than electron. but still we could approximate that the Q was nearly equal to the kinetic energy of the alpha particles. So similarly, the combination of both is going to be nearly equal to the Q of the nuclear reaction. So what is the difference between the neutrino and the antineutrino? The difference is in spin. If one is spinning clockwise, then another will be spinning anti-clockwise. So that is the difference. Otherwise everything is same. The mass, charge and everything is the same, but they are differentiated in terms of spin. So spin is the differentiator between neutrino and antineutrino. Now what are the properties of neutrino? Okay, properties of neutrino is it's massless, it is neutral. The third thing which is not mentioned here has got a spin half. That's the spin. So spin of neutrino is half, it's a fermion like electron. So both of them have got same spin. The difference is it is massless, it is neutral. So now you can, dear students, differentiate between a neutrino and photon. Okay. So what is the difference between the neutrino and photon? The answer is both of them are massless, both of them are neutral. The only difference is this is a boson, while this will be a fermion. This has got a spin half, and this is a spins. A boson has got integral multiple of H cross spin. Now the whole idea is why it's a ghost particle? Massless. Millions and trillions of neutrinos pass through our body, but we don't realize them. It's massless, so the hardly has any impact. It can pass through any object. It can pass through the crust of the earth. It can pass through the space. Neutrinos are emitted in, trillions and trillions and trillions in the nuclear reaction happening in the stars. They are thrown in all directions, and some of them they enter Earth's atmosphere, they pass through Earth's atmosphere, they enter into our body, they enter into the crust of the earth, but still we don't feel its presence. That's why it's also referred to as ghost particles. So dear students, to sum up, what we discussed today was what are the difficulties in understanding the beta decay processes. The difficulties, as we have seen, conservation of energy, conservation of linear momentum, conservation of angular momentum, not satisfied in a beta decay process prior to 1930 was a big problem, and that was something which people could not solve. It was the genius of Pauli who said, introduce a new particle in the equation. So the charge balance, to maintain the charge balance, he made it chargeless. In order to ensure that the Q is not disturbed, he made it massless, he made it chargeless. And he says to explain the Q, he says then who takes away the remaining energy in the energy spectrum is the combination of electron and neutrino accounts for Q. It is not electron alone which is accounting for Q, nor neutrino alone which is accounting for it. It's a combination of the two which accounts for the Q of any nuclear reaction. And the other thing, very, very important thing I think you guys should understand at this stage is alpha problem and beta problems are very different. The alpha particle has got a tunneling handicap. There is a tunneling probability involved. And alpha particles are created much before they are actually coming out of the parent nucleus. While in case of beta particle, it is created at the instant, at the time of its emission. So it is not existing, because all of you know that electrons cannot exist in nucleus. So they are not created beforehand. They are created only when neutron gets, there's a transformation happening because of the weak force from neutron to proton or vice versa. And electron or positron are emitted, and they don't have to face any potential barrier. They are able to tunnel through because of the low mass. And that's why the two problems are different. Their treatment has to be very, very different. And in the future lecture, maybe a lecture, after two lectures or so, we will have to discuss a theory which will have to explain this nature of the graph. This graph has to be explained. Why is this graph like this? Okay, how do you explain this graph? The shape of the graph. If you're able to have a theory which explains the shape of the graph, then our theory is correct. That's what won the Nobel Prize to the great nuclear physicist Enrico Fermi. Thank you.